My name is Pavan Rallabhandi. I'm the Senior Engineering Manager for Private Cloud Storage Solutions at Walmart. My team deals with all things related to Ceph at Walmart. Today, I'm joined by.
Hey, I'm Anton Becker, and I work with Pavan on Ceph and all things Ceph.
Today, we are going to take you through what we've been doing at Walmart with Ceph. It's been a while. We mentioned the number of years that we've been doing Ceph on this slide. It's actually almost a decade. And both of us have had the privilege of seeing through this journey all through these years. We're going to have this presentation split in 3 sections on how it started, how it's going, and what are we looking forward to. Just as yet any other Ceph journey, members from DigitalOcean were also talking about it earlier in the day. We started off with supporting one of the largest OpenStack deployments out there. For persistent block storage offerings, we started Ceph with Library. With a very modest sub 1 TB flash drives, commodity hardware, Ceph runs on everything. That's what we did. Not anything fancy back then when we started. Like it was a single 10 GB networking. And with respect to density of the servers themselves, they are like perhaps like half of what we do today on a single host for an entire server. That modest start with respect to Ceph block was actually pretty decent. It served the needs that for the applications that were onboarded on OpenStack, it served their needs pretty well. We always started Ceph block, always run on all flash. Whereas for Ceph object, we were a bit more adventurous back in the day. This was with releases such as Hammer into like pre-Luminous. Ceph object, we started off more adventurously in the sense we took on the big data workloads on Ceph object. Back in the day, there were not many people who were doing that. And with Swift versus S3 choice that we had, rather again, more ambitiously, we had taken Swift. And to power Ceph object with big data workloads, we had a shim layer almost on the same length as what S3 had, like S3A. We had something called a Swift A, which was eventually open sourced. We have developed and made some feature improvements to RGW to support that pipeline, and we have committed back to the Ceph project as well, which we'll see in the next slide. From that journey, we moved on to multiple release upgrades, all the good stuff with respect to operations. Some of the highlights of the journey was also in-place conversions of level limited OMAPs running on all file store. So all of this was on file store, pre-container era. Lot of learnings from this slide. Now, with respect to some of the quote-unquote old problems, the problems that thankfully are still not relevant in some ways in our current deployment. Ceph object with respect to RGW had its own share of challenges. We ran into a couple of things with RGW. Notably, some of them being bugs with Swift object expiration and out of memory like RGW crashes. We have always co-hosted RGWs with OSDs. Memory issues, sizing of memory for OSD with file store, all the good things with respect to OMAPs and examples, they're all very much relevant for us with Ceph object deployments. And we have run into rather pretty nasty bugs with respect to RGW, almost like leaking data with Swift copy object semantics, specifically to do with Swift copy operations. And then when you delete an object that you have copied, it left back the tail objects. That layer of separate object would be cleaned up, but the tail objects are remaining. And some of the nuances of it wasn't apparent because on the user utilization statistics, they wouldn't show up unless you do some sort of an audit to see whether the pools are itself leaking such data. And then this is all with Ceph, and of course the thread pool sizing, memory issues on these nodes were all, some of these things were like not apparent when you build this at scale, but as you grow and then as these clusters grow in size with respect to utilization and raw utilization, most of these things have beaten us back in some way or the other. So some of the fixes that we have done in all of this, in light of all of this, can be found here. Now from there, so what are we doing now, right? Like, so all of our clusters, whether they are natively built on Quincy or not, we have upgraded most of those clusters from Nautilus to Pacific and to Quincy. This is all orchestrated and with containerized. Our Ceph block journey, while it had been pretty stable, knock on the wood, with respect to Libabili way of doing things, we didn't have a clear signal on what our applications were seeing with respect to latency. Ceph natively didn't have any good metric with respect to end-to-end latency of an IO that is submitted to the cluster. We built a block storage latency monitoring framework that is almost like a canary FIO jobs that run outside of Ceph in our OpenStack environment, trying to mimic what an application would experience on our block clusters. We have tried and built clusters in multiple configurations with respect to number of OSDs per disk, or straddling OSDs across disks, or even splitting disks with respect to more number of OSDs. And there have been some learnings from that too, with respect to performance characterization of the subcluster. And we have standardized on doing certain way of deployments with respect to OSDs per disk. And then we went on to support boot from volume capabilities with OpenStack, which is also powered by Ceph. And we have built the trim and discard support across various virtualization layers, right from our orchestration platform, where we have spun up, to that of OpenStack, Hemu layer, and then further translating to discards, resulting in drive utilization. Most of this has been a work that was not done when we started off, but this is something that we have evolved over the years with respect to increasing the efficiency and utilization of the clusters. From there on, industry pendulum swings have happened with respect to Ceph block and Ceph object. These days, we are looking at high throughput object workloads. We have started to move away from Swift for various reasons. So for some of the reasons that I've mentioned in the previous slide, we have started to adopt more of S3 standard. And our object cluster deployments have not changed much, but we have moved away from, or we are trying to move away from co-locating RWs with that of OSDs. We have, irrespective of the block and object, we have always run OSDs on LVM volumes. We do our custom LVM. Some of the details of it we'll cover in the next slides. We have had our own share of issues with mClock in Quincy. So we've moved away from mClock. We are running WPQ on Quincy. And if you look at our density of our service as on date, it is roughly like 20x higher than what we have seen or what we have built like almost 10 years back. That said, from here on, we'd like to talk about what are our current challenges, how are we tackling them, how are we planning to solve them, or how have we already solved them in some ways, and what are we looking at it in coming years.
So first, I'll talk about some of the Ceph ADM issues that we're seeing. So I think Neha was mentioning how it's wonderful that we have all these tooling available for developers to test the Ceph code, but sometimes it's not enough because what you test on your laptop is not necessarily where you're going to see in production at scale. When you have a cluster that's 100 nodes, maybe 1,000 nodes. We are certainly having a lot of issues with Ceph ADM currently. I would say maybe one of the biggest things right now is that we're dealing with is like undeterministic hardware failures that will trip up the Ceph ADM orchestrator, and it's hard to code, against hardware that is maybe unknown to developers, right? So it's understandable that we're dealing with it now. Perhaps in the future talk we can be more specific about how we're dealing with it, but the main thing that we're doing today that we've decided to do unmanaged OSD. So we deploy nodes with Ceph ADM, but then we don't want Ceph ADM to be constantly making changes. It is challenging sometimes. Ceph ADM will start doing things on its own almost, like in the middle of when there's no maintenance going on. So that's probably the biggest thing that we're doing now. We are still, even on Quincy, we're still dealing with issues with Ceph Manager. When there is a heavier load on the cluster, when the cluster is very busy with thousands and thousands of RBD volumes, lots and lots of OSDs, Ceph Manager can't always keep up, and we start missing metrics with Ceph Explorer. The one other thing that we're dealing with in terms of metrics is Ceph performance metrics. We have, if Ceph Manager falls behind, then when it catches up, you get these like abnormally high readings that don't make any sense. So we have to filter those out, and that's a little bit challenging. There is I'm sure everybody's familiar, there's a Ceph fail command, Ceph Manager fail command. It's great that it's there because it's very easy to run, but we don't think that should be the case. We shouldn't be failing managers to bring things back into normal operations. So we still do that today. We do that for multiple reasons. We don't think that should be the case. Although it's great that we have that command. Obviously, it's very easy to run. The other challenge that we have right now with regards to, again, this is on very large clusters. When you have lots and lots of RBD images, we would like to have more visibility into our clusters, but it's hard to enable Ceph perf metrics on larger clusters because there's a lot of metrics that come out of that, and again, Manager has a hard time figuring out. I want to mention on the previous slide about trim and discard. So with larger clusters, sometimes we get to see larger thunder and herd problems, and it's something that we're, I would say, only now learning how to deal with. There's a couple of approaches that we're doing, but the trim and discard one is certainly, I don't think it's handled by Ceph very gracefully right now. Basically, if you send, if you have a large VM application cluster, let's say 500 VMs, and they all decide to send trim and discards at the same time, that's gonna be really bad for us. The current QoS that we do on the OpenStack sender side doesn't throttle trim and discards, so that flushes down to the sub cluster immediately, and you can have millions and millions of IOPS, and your latencies start shooting up. And so we had to obviously randomize trim and discards. That's now default in Ubuntu VM images, but we can't always control what the VMs can do. So we need better ways of dealing with it from the Ceph side. It would be nice if Ceph could potentially have different QoS settings on different operations. There's a way to filter with like a RBD QoS. You can filter out operations like reads, writes, trims, discards, but you can't apply different QoS settings for different operations. and I already mentioned briefly, but we do sometimes deal with application VM clusters that are but perhaps 500 VMs in size, and sizing subclusters to handle those kinds of workloads when an operator might, like an application operator might, run some command manually or at a schedule, and all 500 VMs start reading or writing at the same time to the same subcluster. That can be a little bit challenging. We have disabled Ceph health device metrics. We love that feature, but it still doesn't work for us. It causes the latency spikes, even in Quincy still. So we don't use that today, although we do like that feature and we do use it on smaller clusters. I'll mention this. So the last 3 bullet points, I'll sort of go into a little bit deeper on the next slides, but on larger subclusters, when we have large numbers of OSDs, we ran into an issue on OpenStack hypervisors where we ran out of ephemeral ports. So I'll give you like a very simple math. If we have 4,000 OSDs and you only have 32,000 ephemeral ports, you can't have more than 8 VMs on the hypervisor mapping a single disk to each VM. So because each VM QEMU process will open up a TCP port to every single OSD in the cluster. So that's a challenge, and we had to deal with it. I'll get into the details a little bit later. So Pavan mentioned in the beginning that we had some RTW issues early on with Hammer days and perhaps earlier at Luminous. Well, we still have RTW issues today. This is the only, I promise, this is the only slide where I'm really complaining. I don't want to sound like I'm complaining too much, but so I did give one specific way to crash an RTW on a Quincy 17.2.7. Yes, it has been fixed in 17.2.8, and I know, yes, officially Quincy is no longer supported, but we were running with this last year, and this is a wget command. So it's an unauthenticated request. So you don't even need a username and password on the subcluster. So this is an actual request that you can run. The only thing I changed was just the word, the host name, the URL. Obviously, it's not Ceph, it's something else. But everything else is literally the same. This is a invalid request, but if you use a valid request, it'll do the same thing. So as soon as I do this, RGLA will crash. Actually, I had a video of how it happens, but it was too quick and it was crashed. But this is an actual thing that you can. This has obviously been fixed, but I don't know how this could still be happening 9 years after we've been running RGLA. So the rest of the 4 bullet points at the bottom there, these are actual bugs that we ran into in the past year. Again, running on Quincy, 17.2.6, 17.2.7. Object expiration link on resharded buckets. So that's if you guys are not familiar, that's if you have object expiration and then a bucket resharding happens, like automatic bucket resharding happens, well, that object expiration stops working, and now you have a data leak, and things are not getting deleted properly. There's a separate bug with object expiration where if you change the expiry settings, those settings don't get honored. Is it also with resharded buckets? I believe so.
Doesn't have to be, as long as you just overwrite an existing hint.
Yeah. We did have a heavy I/O workload where there was a lot of writes and then a lot of deletes happening on object storage, and when those deletes came in, there was a very heavy garbage collection load, and that would crash for deletes. So this is where things like setting up dedicated RTLs only for garbage collection helps. And I think this is still broken. There's an object lock there's a bug with object lock on multi-part deployments. All right, enough complaining. So I wanted to talk about one thing very specific that I don't see. So I've been going through several Ceph days. I haven't seen a lot of conversation on this, but I did finally get validation from Mark Nelson that this is a real issue and that I'm not crazy. So I don't have a lot of very graphical data, but this is very real numbers. So essentially, I'm sure you've seen lots of performance blog posts from Mark Nelson and others in the community about how if you have lots of very fast NVMe drives and lots of CPU power on a 5-node cluster, you can put 2 or 4 OSDs on a very fast NVMe drive, right? And you get better performance. And there's proof that you get better performance, right? However, what happens on a 5-node cluster is not the same as what happens on a 100-node cluster or 200-node cluster. So in the lab, I didn't have 200 nodes, I only had 48 nodes. I did this right before I was actually doing this on the plane last night. There's 4 results here. This is exactly the same hardware. So 48 hosts, 1500 CPU cores. I don't know exactly how much RAM, and same OSDs. So same flash. So there's 10 NVMe drives in the host. But if you start out with a 5-node cluster and you deploy, let's say, 10 OSDs on 1 OSD on each NVMe drive, you'll get very low latency. You can on a 5-node cluster you can get like sub-millisecond, like half a millisecond latency results from a Ceph cluster. But then as you start adding nodes, you will eventually start seeing a pattern where you do see much your latency starts going up. And so this test is basically same exact hardware, but just changing the number of OSDs per node. And with 1 OSD per node, I can still get half a millisecond latency with 48 hosts. When I put 2 OSDs per node, that goes up a little bit. When I put 10 OSDs per node, that goes up. And if I put 20 OSDs per node, now all of a sudden I have almost 1,000 OSDs, and my latency is actually above a millisecond. So the theory here is we actually don't know what this is. I've spoken to Mark Nelson about this. I've spoken to Federico and Dan. I think he's not convinced that this is an issue. But so we think that this has something to do with how network connections get stood up and torn down, and also potentially something to do with like threads within the OSDs. But for us, this is a thing that we have to deal with. There's a question. Go ahead.
I'm just curious. I want to be clear. What latency are you measuring?
Yeah, a good question. So that should be more clear in the slide. So essentially, this is direct sync IO, single queue depth, single thread, right to the Ceph cluster. This is at 4K. Obviously, it doesn't really matter what size you send, but I mean, we measure with 4K. So if you have a low number of OSDs that are participating in your with your client, then you can get much better latency. So I don't have to tear down OSDs and resize my cluster. What I can do is I can have a very small pool where there's very few number of PGs. So if I don't have, let's say I have a test pool with 32 PGs and I have 960 OSDs, obviously 960 OSDs are not participating in my IO, right? So at most, if I'm lucky, it'll evenly get spread across some 32 OSDs within this cluster, and I'll get much better performance. Obviously, aggregated performance is different. If I only have 32 OSDs, I'm not going to get as much IO in total than if I could get with 1,000 OSDs. Yes.
This is one of the OSSOP problems.
Maybe. I don't know.
Okay, that was just my immediate.
Well, so how did we solve this? And this goes back to what Pawan mentioned before, this is one of the reasons why we do our own LVM layer. We don't let the orchestrator do it. So we feed the orchestrator a list of LVM logical volumes that we pre-create, because this abstracts the hardware layer, and we have the ability to change how many OSDs are deployed in a host, but still using all the drives within them. But we still don't know what the problem is, and we would love to figure this out.
You're saying that deploying with LVM solves the problems?
No, the solution to the problem is limiting the scale of a Ceph cluster from the number of OSDs. So Ceph cluster for us, if we want to have a low latency workload, doesn't infinitely scale. All right, well, let me just mention one more thing. We're almost out of time. So the other thing that I don't see a lot of conversation in the community from like other talks that I've seen is latency during failures. So these are just some general, very ballpark numbers. But what we've seen for us going from Nautilus to Quincy, we've actually seen some regressions in these numbers. So when an OSD stops gracefully, PG's peer, and that takes about 1 to 2 seconds. So that's the latency that's the IO stall that your client can potentially see up to that amount of time. Obviously, for one single OSD stop, it's a very small percentage of IO that is affected. For an ungraceful OSD failure, this seems to be a regression for us on Quincy. We can see a latency up to 20 seconds. If we have co-located MONs and OSDs and a MON host fails, this is one of the reasons why you don't want to be running co-located MONs and OSDs is so both MONs and OSDs fail, but the MON election doesn't happen immediately. There's a little bit of a heartbeat timeout. There's some amount of time before MON election happens. Then you have a MON election, and only after a new MON leader is elected, then it was only after that the OSDs start figuring out who is in charge of which PG, right? So this can take up to 40 seconds for us in some clusters, unfortunately. And this is definitely a regression in Quincy. We haven't quite figured out what tuning parameters changed or what we need to change. But this went from about 15 seconds on Nautilus to like 20 to 40 seconds on Quincy. And perhaps the last thing that he'll mention is once a year we'll run into some hardware issue where hardware doesn't go down gracefully, and you will have a latency that could be measured in minutes, essentially an average. Usually it happens with like a flaky OSD, and actually just like I think last week or within the past 2 weeks, we had a actual like CPU machine check error. Usually when we get machine check errors, the machine just goes down. Well, in this case, half the OSDs went down, half the OSDs kept running, and the cluster was not happy. And so we need to figure out better ways how to deal with these kinds of ungraceful, undeterministic hardware failures. So anyway, this I would say for us it happens maybe once a year, and we every once in a while we find these new ones. This machine check error that just happened. That's certainly a new one for us, because usually those just bring the host completely down. I think we're out of time. We can talk more in future talks.
Maybe you can show the next slide.
Just really quick, do you want to quickly talk about it?
Yeah, in the interest of time, like
with all of this, right, we are looking forward to having low latency workloads for sure on Ceph block more and more. While we have, like with the sort of the technology that we have built over the years with respect to running this large scale Ceph clusters, relatively speaking, we are looking at potentially like error reporting for block, and also Ceph CSIs. It is one of the things that we're interested in. So, yeah.
Cool. All right, thank you.